You are watching this video through the internet. Today, this is how we store most of the video information we watch everywhere. But that was not always the case. In the 2000s, the most popular format was CDs and DVDs, metallic discs that stored information, such as music and movies. And the films were distributed in this format through the so-called video rental stores, which were essentially film libraries. This is how the ancient Mayans used to watch movies. Before CDs and DVDs, the best format for distributing music and videos was Betamax tapes. And most likely, not even people who were old enough to remember videotapes will remember Betamax. This is because even though it was the best format, the most common format was VHS tapes. Betamax tapes were better than VHS tapes when it came to information storage capacity and video quality. However, this technology never reached the market widely. The technology that was objectively the best ultimately lost the race to the market. In the case of something like film storage tapes, the ramifications weren't so dramatic. But today I'm going to tell a similar story of a choice with much deeper consequences. In 1955, we chose to invest in the wrong nuclear power plants. And this choice was reinforced for decades, ignoring the safer and less problematic option for nuclear energy production, which are liquid fluoride thorium reactors. There is an alternate timeline in which the worst nuclear accidents like Chernobyl and Fukushima were avoided, and in which the nuclear waste that will last 10,000 years is not a problem. And unfortunately, we do not live in this timeline. Today, we will understand the choice that decided the future of nuclear energy in the world. In the 1930s and 1940s, humans learned about the uranium atom. One discovery was that neutrons can break its nucleus. Neutrons are neutral particles in the atomic nucleus. When struck by a neutron, uranium undergoes nuclear fission. During fission, the uranium atom breaks into lighter atoms, releasing energy and more neutrons in the process. And these neutrons in turn can strike other uranium atoms, releasing additional energy and additional neutrons. By assembling an adequate quantity of uranium atoms close to each other, you can create a situation in which the fission of one uranium causes one or more fissions of other uraniums. And this is a chain reaction. If you do this in a controlled manner, you can create a mass of radioactive material that emits large amounts of heat. And this heat can be used to evaporate water, and the evaporated water then spins the blades of a turbine connected to an electric power generator. This is how a nuclear reactor works. Or if you do this with the right type of uranium, much faster, you have a nuclear bomb. Not all uranium atoms are identical. Some have different numbers of neutrons in their nucleus, known as uranium isotopes. This is a crucial detail to understand. The most common isotope found in uranium ore is uranium-238, but it is very stable and does not break easily. In other words, pure uranium is not effective for bombs or nuclear power plants. The ideal uranium for energy production is uranium-235, which is more easily broken. Nuclear power plants use enriched uranium ore, in which the concentration of uranium-235 in the ore is artificially increased from 0.7%. which is the natural level, to something between 3% and 5%. For bombs, we need enriched uranium to be over 80%. The goal of nuclear research during World War II was military use in the form of a bomb. Thus, all nuclear research focused on plutonium and uranium, elements that are useful for a bomb. Plutonium is element 94, and it is especially useful for nuclear weapons. In addition, plutonium does not naturally exist in abundance. It is produced in uranium nuclear reactors. This part is important, so store it for later. However, outside the spotlight, there was a third element capable of producing nuclear energy, thorium, which is element number 90. Thorium does not suffer fission like uranium, but it can be utilized in a breeder reactor for indirect fission. The thorium atom changes to a uranium-233 atom when hit by a neutron, and it is this uranium produced by thorium that undergoes fission, releases energy, and generates more neutrons. And then, these neutrons can hit more thorium atoms and continue the cascade of energy production. This thorium and uranium-233 cycle can be the basis for a nuclear reactor, but not for a bomb. Another crucial point I want you guys to keep in mind: thorium reactors were favored by key physicists in the field of nuclear energy, including the father of the hydrogen bomb, Edward Teller. Probably the biggest proponent of this technology was Alvin M. Weinberg, the director of Oak Ridge Lab from 1955 to 1973, where uranium reactors were used to produce plutonium for nuclear bombs. Both Teller's and Weinberg's careers relied on the production of plutonium, and both were strong supporters of a nuclear energy technology that did not generate plutonium. So, what do thorium reactors have in them that made even those who worked with other reactors like thorium ones so much? To understand why thorium appeared so incredible, we must learn the issues and risks of traditional uranium-based reactors. Traditional uranium nuclear reactors utilize solid nuclear fuel. It is cooled by high-pressure water, and its power production is managed by control rods. And each of these parts of the process has a different problem that a thorium reactor does not have. Having uranium as a base element implies the production of long-lasting radioactive elements through neutron capture, which remain dangerous for thousands of years. And the fact that uranium is contained in solid fuel implies that these hazardous elements are formed within the solid fuel material. This makes it hard to separate unwanted elements from nuclear fuel. In addition to long-lasting radioactive elements, the process also produces contaminants, reducing the reactor's efficiency. So, it is necessary to regularly change the solid fuel. The cooling of usual reactors is done by high-pressure water, which enhances the negative consequences of accidents. Gases or liquids under high pressure are fundamentally explosive. While they do not lead to a nuclear detonation, they can enhance the damage caused by other accidents and aid in the spread of nuclear material in the region surrounding the accident site. If a uranium nuclear reactor is left unmoderated, without the direct action of a material that reduces the rate of nuclear reactions, the tendency is for a nuclear meltdown to occur, and the chain reaction in the reactor gets out of control, causing a nuclear catastrophe. The reactors proposed based on thorium are completely different. They are reactors that use the thorium and uranium-232 or 233 cycle with molten salt fuel at low pressure. A liquid, just operating at low pressure, already removes the problem of a high-pressure system that can enhance accidents. And the thorium cycle with uranium does not produce radioactive elements that last thousands of years. They last a few centuries, which is a significant improvement. And besides, the liquid salt fuel needs to be kept at high temperatures for the reactor to produce energy. If any accident happens or the reactor goes out of control, the tendency is that the liquid will simply solidify and the reactor will cool down instead of melting. On the other hand, if the liquid with the nuclear fuel gets too hot, it expands, pushing away the uranium-233, which produces neutrons, from the thorium, which produces uranium, reducing reaction efficiency, cooling the reactor. In other words, in the event of overheating, liquid fuel nuclear reactors have a tendency to cool down on their own. Pressurized water reactors are constantly working to prevent a potentially devastating catastrophic meltdown event, and liquid fuel reactors such as thorium are struggling not to be shut down alone. So here we kind of already see a clear advantage. But wait, since nuclear fuel is in liquid form, we can separate impurities and problematic elements through chemical filtration, which means that treating liquid nuclear fuel is much less laborious. Another factor is that this reactor can utilize nuclear waste with an extended lifespan to generate energy, transforming waste that persists for millennia into waste that endures for centuries. Liquid thorium reactors not only avoid the problem of long-lasting nuclear waste, but can actively help solve it. And just to make it clear, there are liquid fuel reactors that use uranium, but thorium has advantages over it precisely because it produces a less problematic type of nuclear waste. Another important detail is that thorium is 3 or 4 times more abundant than uranium. India is one of the main countries interested in developing this technology precisely because they have few reserves of uranium, but many of thorium. And to top it all off, it's harder to use thorium reactors to make nuclear bombs, especially the plutonium needed for thermonuclear bombs. What it means is that it is a safer reactor to be developed in international collaborations, in which nuclear espionage can be a problem. So, if this reactor has so many advantages, why hasn't it become the dominant reactor? There are 2 reasons, and both are outdated reasons for this. In 1955, the USA's Admiral Hyman G. Rickover was in charge of the development of nuclear submarines, and he had a crucial decision to make. What reactor type would be developed for nuclear submarines? The options were thorium, uranium, and plutonium. Rickover probably didn't know at the time, but his decision changed the future of nuclear energy. The Admiral chose to invest his resources in creating uranium-based nuclear reactors. And he had 2 reasons for that. The first is that, at the time, uranium reactors were indeed more efficient. And since the reactor would have to be miniaturized to fit in a submarine, it was a natural choice. However, the primary reason uranium reactors were more efficient is because we had more research on these technologies than the alternatives. There is no fundamental reason why uranium reactors are more efficient, particularly for power plants that are situated outside submarines. The other reason is uranium reactors produce plutonium. and plutonium is essential for nuclear bombs. Accelerating uranium reactor technology would have a dual use and also accelerate the production of nuclear bombs. None of these reasons are valid in today's world. But this decision initiated a chain reaction of decisions favoring uranium reactors over thorium reactors. Influenced by Rickover's decision, the first commercial nuclear reactor used uranium, and as a result, it didn't take long for a lot more physicists and engineers to specialize in uranium reactors than in alternative technologies, which meant that it would be cheaper to continue developing and creating uranium-based reactors than to look for alternatives. And this further increases the discrepancy in expertise and price between uranium and thorium reactors. Gradually, the interest in thorium faded and uranium reactors became established as the primary method to generate nuclear energy. In the United States, research on thorium reactors was basically halted in the 1970s and only resumed more recently. What decided the modern form of nuclear energy production was not a coldly calculated decision, but a spur of the moment based on military and media interests. But research on thorium continued to thrive in countries like India. They even built an experimental reactor that used thorium in the late 20th century, called Kamini. China has also completed an experimental thorium reactor named TMSRLF-1 in 2021, and it is anticipated to commence permanent operation in the coming decade. There is still interest in thorium, but this technology is far from being commercially viable. Decades of development and investment in uranium reactors have made uranium more accessible and less expensive. In fact, modern uranium reactors are much safer than the first generations of similar reactors in the mid-20th century. But if they were made of thorium, we wouldn't have the unresolved problem of nuclear waste. So the question that remains is, can thorium somehow turn things around in the rest of this century? It isn't impossible, but it is also not likely. It seems we have made the decision to continue with the VHS tapes of nuclear power. Honestly, the best scenario is to develop nuclear fusion, which in this same analogy of VHS would be like Blu-ray. Thank you very much and see you next time.